Like fire.
This is Danny. Danny's the one allowed to get the first question.
Okay, I think we're ready to go. What's the matter? Okay. The camera is there, so I think the light's on, so I think that just means, yes, we're on camera. Okay, well, welcome everyone to the December meeting of the Royal Astronomical Society of Canada, Winnipeg Centre. We have a full agenda for you tonight, and we're going to be giving away some telescopes, which is a real joy for our center. It's something we've been doing probably for the last 4 or 5 years, and it gives us a lot of pleasure to do it, and also to see new faces start to take on the hobby that we love here so much. So welcome. We have some early announcements. The arrows aren't working. Oh, there we go. Okay, just some brief announcements before we get started with the telescope for kids and offers. We have a few folks that do volunteer things for the center and keep things running, and I just want to acknowledge them here. Our fundraising committee by Wing Kwong, he's over here. Exploring the Universe, and I think it's Stan Wrench. If you're interested in a new person, or even an old person who wants to take on Explore the Universe certificates, it's Stan Wrench. I think we lost Mike Caracas to NGT. He doesn't need any more airplay. And otherwise, he's the fellow who has the keys to our lunar scopes. So once you get the bug of astronomy and are interested in testing out a variety of telescopes we have in our inventory, right from kind of smaller Dobsonians up to Cassegrain telescopes, 8-9 inches big. We actually have a 12-inch in our observatory, and then we have a 14-inch that's on stilts, or not stilts, but separate legs. So I mean, we have some aperture in our club, but we want you to get the feel of the game as much as you can before you invest your hard-earned dollars. So that's what the Telescope Lunar Program is all about. We also happen to have a C-Star, which is a hot demand item. So make sure you get a hold of Mike. I think if you look at the website, he's on there under Lunar Scope programs. Workshop ideas, we're back to Stan again. Thanks, Stan. And of course, we're always looking for volunteers to help us out with our observatory, with different outreach events and different activities of the club. This year also, we're looking at scheduling some things in the future. Coming up in January, which if you can believe is just under a month away now, we have our potluck. So actually it's not under a month, it's a month and 5 days. So January 10th, we'll have a potluck at scheduled for us with Wing has booked a room at the Grain Exchange for us, same as last year. So please make the time on January 10th. It's a Saturday to join us at our annual potluck. And of course, coming up in March, we'll have our annual general meeting. So always an exciting time, our annual general meeting. And we also have, oops, I'm going to shrink this down a bit, but Dennis Lyons has offered to train us on green laser pointer work. So either to be a green laser pointer guide. Dennis not here, unfortunately. I think it's too big, so I'm not sure quite how to shrink it.
You can't move that bar at the bottom.
Okay.
Grab it.
Just grab it and drag it.
Yeah.
Now we're still, I can't really, okay, it shows up a little bit better. And so yeah, Dennis has offered to do green laser pointer training December 17th. So there'll be more in the main list once we have that finalized, and there'll be a link. All the training is done electronically online. Dennis guides us through it, and he has experience with Transport Canada and puts on a really excellent course for us to get green laser pointer trained. And once we have the training, you can be both a spotter and actually use green laser pointer to put on a show for for colleagues, friends, different other groups. But again, once you have your training, then you understand kind of where you can do it. Because there are tight restrictions on the use of green laser pointers. Okay, without further ado, I think this is just our celebration plan for January. It's on Grain Exchange Building, and now I've got the bar in the wrong place again. Okay. Anyway, at the launch co-working, it's at 500 167 Lombard, same as I think last year, and we'll start around 6 p.m. Now the kind of the thing that probably some of the newer folks here are most interested in, we're going to move on to our Telescope for Kids presentations. Okay, so we have 5 here tonight, and if we could ask them to come forward, we'd like to present them with a telescope. So Jessica and Vivian, you would come forward. Lila, Nika and Zara, Mackenzie, and Shia. Okay, great. Okay, if I could have the Telescope for Kids committee come forward, please. Okay, I'll just give you a quick introduction to our committee. Okay.
Committee.
Yes, we had a committee. So Wing Fong was involved in the committee. Come on up, Wing. Yeah. Judy Anderson.
Yeah.
James Fast is seated in the corner, and myself, Mark Irvin. So we coordinated this event for this year, and we have 7 winners, 5 of which could attend tonight, and we're pleased to present the 5 telescopes. So I think we have 4 telescopes in paradigm. Yes, correct. So we'll look at the larger one there, perhaps. I think that's Jessica Vivian, who was the 16-year-old.
No, the dog was for the oldest. Yeah, oldest. So that's Nika and Zara, right?
Nika? Who is the oldest?
My sister was very sick.
Oh, yes. Nika or Zara?
Okay.
Nika. Okay, so this is for Zara.
So what we're gonna
Both of them.
For both of you.
yeah. So we're already kind of one scope
For the sisters.
For
per
family.
family.
Okay.
So this is a telescope that was donated, and we just had to clean it up a little bit. These are all fantastic telescopes. These are amazing starting telescopes. They're way better than you would buy at a department store. I tested this telescope. I had to clean it a little bit. I tested this telescope, and we have more of these in our club. These ones, Saturn, the planets, look amazing in these telescopes. You can see all different kinds of things.
Features on those planets, yes.
So these are all, they're called Dobsonian type of telescopes, right? So what you do is you put your eyepiece in here. We're gonna go into the hallway in a little bit. We're gonna kind of go over all of this with you, show you kind of how it works. But you'll end up looking through here, and the light is gonna come in at this end. And if you look down through here, they're all gonna be the same. So we're gonna have some, if you look kind of down there at the end, there's a big mirror right at the end. You can see that? See that here? So that's the light from the planet or from the moon, stars, or stars. They're gonna come, they're gonna bounce off that mirror, and they're gonna hit another mirror that's right inside here. You're gonna look at that picture. You're gonna use this to focus. We're gonna go inside into the hallway there and go over all of those.
And they're all basically the same design.
All basically, this one sits on the floor. It's bigger. Yeah, so we thought, this one, you're a little bit older, you can handle maybe the bigger one a little bit easier. These ones just sit on a table like that and are a little bit easier to move around.
Okay.
Yeah.
And so these are all similar design as this. These have a base. They come in a box at once, then they extend out. I'll show you what the design. Okay. So I guess what we should say is the binoculars go to the eyepiece.
We're gonna go to Mackenzie. And what's in the bag, Wayne? So each telescope is coming with a bag of goodies, and we've got all kinds of meeting kits in here and a whole bunch of stuff. Are you ready? Okay, so there's your bag. Can you hold on to that? And we'll go back there. Perfect. I don't know, Ross, do you wanna get a picture? Where's Ross?
I'm right here.
There he is. Okay, you better go look at your desk. Is that okay if I'm in the picture too? Oh.
Hey.
Perfect. Awesome. It was a very good entry that you made. Thank you very much.
Take your picture.
Okay, so, yes. You wanna stand right beside that?
Thank you.
Okay, let's get this out of the way. Okay.
Might as well take it out into the hall.
Sure. I'm gonna give you that.
And then we have Jessica and Vivian. Well, that's for you.
And we'll open them up in the hallway.
Side.
Yes, that's it. They will open them up in the hallway and we'll explain how they all work. Okay, so, great. Now we have.
And then we have the.
Delilah. So stuff. Aaron. Okay, that's fine. You stand.
Everybody did a great job with the applications.
Yes. Great smile. Oh, yes. They're just starting the making. Yes.
Okay, and Shaya.
Shaya. Okay.
Well, there you go.
Okay, so once you have your picture, you can get mine. Pardon me?
How are you?
We'll open them up in the hallway and then we'll open them up and we'll get them going. Okay, sorry. Is it Shaya or Shaya?
Sure.
Shaya, yeah. Okay,
Okay,
congratulations.
okay, congratulations.
Okay, so we can, everybody, so as this telescope, we can take them out in the hallway. We're gonna adjourn the meeting briefly while we go out in the hallway to help the young ones and the students get the telescope started. Open it up and explain a bit to them.
So let's say something to the Zoom people, but.
Sure.
Take the slide out there.
So Zoom folks, we're gonna cut out for about 25 minutes or so while we help out with telescopes for those telescope kids winners. We'll see you in about 25 minutes. Thank you. everybody gets excited. So,
Camera's on.
thank you. So I'm not on camera probably.
Get it outside.
Well, we got the moon actually through the window.
Well.
Yes. Yes. Okay. So I think I'm on camera. And we will be starting very shortly as soon as everybody gets back in, and the next it's coming. There we go. Okay, well, the first thing, I guess, once we have everybody back in, is going to be Gail Wise with our beginner session, and she's going to speak about Gemini. So we'll give Gail a bit of time to get set up. And for the rest of the folks that are kind of all jazzed up with their new equipment, time to get back. And we'll begin. Here comes Gail with talk. Thanks, Gail. Yes.
Yes, you're all ready to go.
Shall I start or shall we wait for people to come in?
I think you may as well start. I think we've got. Yeah, go ahead.
All right.
Thanks, Gail.
To a lot of ancient people, this constellation was seen as a set of twins. One of the oldest stories about Gemini is a Hindu one. How do I advance? When Surya, the sun god, got married, his wife was so exhausted by the dazzling interest he took in her that after a while she couldn't stand it any longer, and she had to leave him. She ran away to the forest to live as a mare. That's a lady horse. But Surya missed his new bride so much that he just had to go out and find her. And when he did, he turned himself into a horse too and married her again. As a result, she gave birth to twins, known as the horsemen. They are eternally young and handsome, and they ride across the sky at dawn. To the Greeks, Gemini were the sons of Zeus, Castor and Polydeuces. Pollux is the Latin form of his name, and that's what the Romans called. Now, no one is really sure whether both of them are the sons of Zeus because of the unusual circumstances of their birth. Their mother was Leda, the queen of Sparta. Zeus was smitten with her, and one day he visited her in the form of a swan. After he had entered her home, he turned back into himself and seduced her. That same night, Leda also slept with her husband, King Tyndareus. As a result, Leda gave birth to 4 children, 2 sets of twins. The children of Zeus were Polydeuces and Helen, who would later become famous as Helen of Troy, and they were immortal. The children who were fathered by Tyndareus were Castor and Clytemnestra, and they were mortal. Castor and Pollux grew up as very close friends. Castor became a famous horseman who taught Hercules how to fence, and Polydeuces became a famous boxer. These inseparable twins joined the expedition of Jason and the Argonauts in search of the Golden Fleece. See how these constellations all connect with each other? They landed in a region of Asia Minor that was ruled by Amycus, who was the world's greatest bully. Amycus would never let anyone leave his country until they fought with him in a boxing match, which he always won. Amycus stomped down to the shore where the Argo was docked and challenged the crew to put up their dukes against him. Polydeuces was disgusted at his arrogance, and he accepted the challenge at once. The two put on leather gloves. Polydeuces easily avoided the fists of his opponent, like a matador sidestepping a charging bull. Then he struck Amycus on the head and splintered his skull. On the way home, there was a terrible storm at sea. The Argo was in great danger. Castor and Polydeuces prayed to the gods for safety. The storm ceased, and stars appeared on top of the brothers' heads. From this incident, Castor and Polydeuces became known as the patron saints of voyagers. Castor and Polydeuces met their ends in a quarrel with another set of twins over a couple of women. What else? It ended when Castor was run through with a sword by his rival. Polydeuces grieved for his fallen brother. He asked Zeus to take his life and give Castor his immortality. Zeus was so touched by his son's devotion that he placed them both in the sky as the constellation Gemini, where they are inseparable forever. The Native American people have a very complex and thought-provoking set of beliefs and traditions in which the legend of heroic twin brothers is often shared and found in many of their societies. In the myths of the Navajo people, these twins are known as Monster Slayer and Born for Water, and they are central figures in their mythology. They symbolize themes of bravery, protection, and the struggle against evil. Their story is not just a tale of heroism, but a complex set of cultural beliefs, values, and the enduring relationship between the Navajo people and their environment. The tale of Monster Slayer and Born for Water begins with their mother, called Changing Woman. She was one of their most sacred deities. Changing Woman represents life, fertility, and transformation. According to this story, she conceived the twins when the sun gave her 2 pieces of turquoise and abalone shell, which transformed into the twins. Changing Woman raised her sons on a mountain where they learned about their divine heritage and the destiny that awaited them. As they grew older, Monster Slayer and Born for Water became aware of the many monsters that plagued their people. These monsters were the personification of chaos and danger in the world. They were determined to rid their land of these threats, and the twins embarked on a perilous journey to the sun's house to seek guidance and weapons. Their journey was filled with challenges, including crossing a vast desert and overcoming numerous obstacles that tested their courage. When they reached their father, the sun, they underwent a series of trials to prove their worthiness. Impressed by their determination and bravery, the sun bestowed upon Monster Slayer and Born for Water. Monster Slayer got a magical bow and arrows, and Born for Water received a protective staff. These gifts were necessary for their mission to defeat the monsters. Armed with their new weapons, the twins returned to their homeland to confront the monsters. Monster Slayer took the lead in the battles, using his bow and arrows with deadly precision. His brother, Born for Water, played a supporting role, using his protective staff to aid and defend Monster Slayer. Together, they defeated numerous fearsome creatures, including the giants, the monsters at Shiprock, and the notorious Yetzo, the big giant. Each battle was not only a physical confrontation, but also a spiritual one. The twins relied on their wit, bravery, and the teachings of their mother and father. They invoked prayers and rituals to ensure their success, highlighting the deep connection between the physical skill and their spiritual strength. The story of Monster Slayer and Born for Water is more than a grand adventure. It is a cornerstone of Navajo cultural identity. The twins symbolize the triumph of good over evil, the importance of bravery, and the necessity of working together for the greater good. One of the most significant ceremonies associated with the twins is called the Enemy Way. This healing ceremony is performed to restore balance and harmony for individuals who have been in conflict or war. The story of the twins is recited during the ceremony, emphasizing their role as protectors and healers. The twins' journey and victories also serve as metaphors for overcoming personal and communal challenges. The name Gemini is Latin for twins. We find them east of Taurus the bull and west of Cancer the crab, with Auriga and Lynx on the north and Monoceros and Canis Minor on the south. Orion is just to the southwest. Gemini is prominent in the winter sky. It's very easy to find the twins by the two brightest stars, Castor and Pollux, that are just east of the familiar V shape of the Hyades in Taurus. Castor is the northern star, and it's slightly fainter than Pollux. Castor is pure white, and Pollux is more golden yellow. The way to remember which is by the first letters of their names. Castor is on the same side as Capella, which is the brightest star in Auriga the charioteer, and Pollux is closer to Procyon in Canis Minor the small dog. Castor is 45 light years away, and its magnitude is 2.9. To the naked eye, it looks like an ordinary star, but in a telescope, you will see that it is a double. And in a really, really big telescope, you'll see that it's a triple. Each of these stars is a binary, which means that Castor is really 6 stars when it looks like one. Each star is in a very close orbit. Pollux is labeled beta, which would indicate that it's fainter than Castor, but that is not the case. Pollux is magnitude 1.16. It's about 35 light years away from us. It's about 11 times the diameter of the sun, and it's about 35 times brighter than the sun. Castor and Pollux are the stars that you will be observing for your Explore the Universe list. Gemini has a small, bright planetary nebula, NGC 2392, called the Parca Nebula, or the Clown Face Nebula. It's also called the Lion Nebula. It's bluish-green in color, and its magnitude is 8.3, which is quite bright for a planetary. It measures about 47 arcseconds in diameter. The central star in this nebula was the very first central star of a planetary nebula ever to be discovered. And it really does look like it could be somebody wearing a parka with a furry hood, doesn't it? Now, when I think of something furry, so if I was naming it, this nebula was discovered by Sir William Herschel on January 17th, 1787. He described it as a star, 9th magnitude, with a pretty bright middle, nebulosity equally dispersed all around, a very remarkable phenomenon. These filaments are a light year long, and it's about 6,500 light years away. There's another planetary nebula in this area called the Medusa Nebula. This measures 10.2 by 10.2 arc minutes, and its magnitude is only 16, so it just looks like a star. You'll need to star hop to find it, and you'll only know that you have found it by the star patterns around it. Gemini is on the east side of the winter Milky Way, and it's very rich in stars. There are a few faint galaxies in this area. One of them is NGC 2339, which measures 2.4 by 1.45 arc minutes, and its magnitude is 12.3. You can find it with an 8-inch telescope, but look at its location. I hope Pollux didn't want to sit down. Our twins also have IC 443, also known as the Jellyfish Nebula. This is a supernova remnant, and its magnitude is 12, and it measures 40 by 50 arc minutes. So it's really very big. But because its magnitude is spread over its entire surface area, its visual magnitude is only 20. So you won't see it visually, only with photography. Gemini has a very nice open cluster, M35. This is 2,200 light years away from us, and its magnitude is 5.1, so it's very bright, easily visible with binoculars. It was first recorded by our friend Charles Messier in 1764, but it must have been observed much earlier by other people. Stellarium calls this the shoe buckle cluster, so it obviously was known back in the days when they wore shoes with shoe buckles, although I doubt Castor and Pollux did. M35 has 120 bright stars, brighter than 13th magnitude, and on very clear, dark nights, you can even see it naked eye. It covers an area 30 arc minutes across, which is the size of the full moon. Now, those of you who know me know how much I like open clusters, and right beside M35 is another treat for Gale. At the southwest edge is a smaller, fainter open cluster, NGC 2158. Its brightest stars are 16th magnitude, and its total magnitude is 8.6. This is one of the most distant known clusters. It's about 16,000 light years away, which is 7 times further than M35. So we know that these two are not related, even though they look like they're right beside each other. NGC 2158 is only 5 arc minutes in diameter, and because it's so small, when it was first discovered, it was first thought that it was a globular cluster. But now we know better. M35 and NGC 2158 are on your Explore the Universe list, so be sure and take a look at them. NGC 2129 is another nice little open cluster. It measures 3.9 by 3.9 arc minutes, and it looks like a cat's paw, doesn't it? Its magnitude is 6.7, and it appears to be about 10 million years old, which is actually very young in the world of stars. And we also have NGC 2266. This was discovered by Sir William Herschel on December 7, 1785. This is a fairly rich cluster, and the stars can be easily resolved in a telescope. It measures 4.2 by 4.2 arc minutes, and its magnitude is 9.5. Another one is NGC 2331, which measures 4.8 by 4.8 arc minutes, and its magnitude is 8.5. So you should be able to see this one easily with your binoculars. NGC 2355 is also known as NGC 2356. I don't know why. It appears to be about 1 billion years old. It measures 6 by 6 arc minutes, and its magnitude is 9.7. And I wasn't able to find any more information about this, which surprised me because it is so big and bright. And we also have the Geminids meteor shower coming up later this month. It's active from December 1st to 21st, and it will peak this year on the night of December 13 to 14. This is caused by debris from the asteroid Phaeton, and it's considered by very many people to be one of the best meteor showers of the year. The hourly rate is hoped to be about 110 to 150, which is a couple every minute, and the moon should not interfere this year. It will be a waning crescent, and it will rise about 1:30 a.m. So let's hope the sky will be clear for us. Be sure to dress very warmly. It is December, and don't go out by yourself. 2 planets were discovered in Gemini. William Herschel discovered Uranus near Eta in 1781, and this is where Clyde Tombaugh discovered Pluto in 1930. Oh, oops, Pluto isn't really a planet, is it? But it was when it was discovered. So with all this neat stuff in Gemini, bunch of open clusters, meteor shower, planets, and even a kitty cat, you must go out and take a look at it. Actually, right now, Jupiter is in Gemini, so you've all been looking at this constellation, whether you realize it or not. The end.
Jason.
Thanks, Gil. Okay, next up on our list is What's Up, What's New with Jay Anderson. There we are. Oh.
Are we on?
I think we're on that.
Okay. December is always one of those transitional months where you can't really hope for warm weather. All you can hope for is a little less than cold weather. But the forecast for the next 2 weeks isn't very encouraging in that. There's lots of nice things in December skies, however, but we're getting away from the Milky Way, so you have to look a little harder to find them. So what have we got? Well, right now we got a pretty big sunspot that's worth a look with any kind of filtering that you can arrange. And in fact, it's one of the biggest sunspots in the last, since the peak of the last solar cycle or before. We got two comets in the sky that we've been following for a couple of months now. We reached the solstice on December 21, which means the sun starts coming back and the nights start getting shorter. But it's actually not until about January 21 that we hit the coldest day of the year on average. We got an impulsive Regulus in the moon in a couple of days coming up. We get the Geminid meteor shower that Gail mentioned, and we also have the Quadrantid meteor shower early in the new year, and a little bit of play between the moon and the Pleiades, although not nearly as spectacular as it was last month when they were over top of each other. So here's what the sunspot group looked like 2 days ago, and it's now just a little more central on the solar disk. If you can see the sun through a bit of thin cloud, you'll easily see those sunspots by eye. And if you've got a solar filter or leftover eclipse glasses from earlier in the year or in the past few years, we've been handing them out quite a bit, then you'll be able to take a look at these and see it by eye. And it's worth it just because it is so big and so easy to see. We get into the night sky. We've got a little bit of we're sort of in a conundrum in a way. Let me pull up a laser pointer here. The Milky Way in December is the summer part of the Milky Way is now disappearing into the western part of the sky. And by the time we get a month later in January, it's pretty much rotated out of sight to the northwest. And all that's left of it is the part around Cygnus, which is still pretty nice, but even that's starting to get low in the sky in a direction most of us spend our time looking to the south. So what instead we have is this part of the Milky Way coming up and being more prominent now in the east and southeast skies as the month goes on. And that part of the Milky Way doesn't have all the nice nebula that this one does, but what it does have is a lot of other sort of finer objects in there. Among them is the open clusters that Gail talked about, because here we have Gemini right here and a little bit farther back. These are for 10 o'clock or rather 8 o'clock in the evening. So of course, these will be rising higher through the night. And the big thing is most of us will be the constellation of Orion, and those of got new telescopes. The nebula there just under the belt of Orion right in here is really worth having a look at, because in these little telescopes it looks really spectacular to watch all of those bright stars with all of that ghostly nebula all around it. As far as stars are concerned, the most prominent one is Capella here in Oregon. And we'll take a little closer look at that later on. So we're into the Milky Way for the next few months, but in behind it, we're starting to run into Virgo. So later on in the night, everything will be moving over this way, and Virgo will be moving up where you see Gemini and Jupiter right there. And in that case, you'll be looking well away from the Milky Way. We'll talk about that as next month comes along. So we look up in near Capella. It's hard not to find Capella. It's the brightest thing in that part of the sky. And underneath Capella, or off to one side, depending on where it is, the sky, find three of these nice open clusters, Messier 38, 36, 37, and Gail already mentioned that 35, I think it was, or was it 39? But these are bright and easy to find open clusters. Binoculars often show both of them at once, and you can just switch around. But you know, the whole of this bowl of the constellation is full of open clusters. So many, I think sometimes that becomes a bit difficult to identify them one from the other. It just looks like a lot of stars in that area. And here we have a picture of M38, and you can see how the clustering, as you scan across the skies, these are going to pop up in your binoculars as little concentrations of stars. We also have this thing called the Flaming Star Nebula for those of you that have automatic telescopes or like to do astrophotography. It's a nice target, but it takes a little bit of exposure to see it. It's got some nice structure in it here, like this picture. Every time I do these, I go looking through my picture archive, and I usually find I've photographed them, but I've never processed them. So I always have to process a bunch of them. Anyway, we look at the planets. I guess the best thing you could say about the next month is that everything seems to be behind the sun. So Mercury right now, in fact, is at its best location on the 7th. I had a picture from last week or last month. You can see that Mercury in its orbit around the sun is down here, is at its farthest point away from the sun, which means that it's easiest for us to see when that happens. But by the time we get into January, it's got too close to the sun and it's not visible. Venus is behind the sun and stays there, and Mars is behind the sun and stays there, and directly behind the sun on the 6th for Venus and the 9th for Mars. But Jupiter and Saturn are both pretty nice in the sky. Jupiter especially, it's pretty much up for the whole night, right through the 2 months. And in fact, gets to opposition, meaning directly opposite the sun. So it's at its closest, and so it's 47 arc seconds in size. So that's a pretty decent size. That's about the limit of the human eye. So people with very, very keen eyesight can see Jupiter as a disk if they're above average in visual acuity. Usually that means they're younger than 20 years old too. Saturn is getting off toward the southwest, and it gets a little lower as time goes on through the month, but the rings are opening up to about 2 degrees from about a half a degree or 6/10 of a degree in right now. Uranus is also up all night long. The only thing that's sort of noteworthy of that is that it's close to the Pleiades, and you could probably use them as a target to get into the area for seeing the planet. Neptune, of course, will take a telescope to see it, but it's also following behind Saturn. So all 4 of these planets are up through a large part of the night and worth observing. We have December 10, Regulus passes just under the moon. I mentioned that last month. It's just coming up now in a couple of days. Just about everybody else in the country, Regulus goes behind the moon, but it doesn't here. There is a grazing occultation of Regulus, which means that the moon just skims along the edge of the sun, or the star skims just along the edge of the moon. And if you're in exactly the right position, you can watch it fade in and out as it goes behind mountains on the edge of the moon and comes out again in the valleys and goes behind. Depending on where you were, it might disappear several times and then wink back in or not. To see that, you have to go about 300 kilometers north of Winnipeg. I somehow don't think there's going to be too much enthusiasm for that. Sit out in a cold night in the middle of nowhere, which we've done, haven't we, Jerry? Yeah, okay. Gail mentioned the Gemini meteor shower. We have a bright moon on that night. Or it's it's bright on the latter half of the night. The beginning of the night is pretty good. And because Castor and Pollux are rising, and they're in the map I showed you, they were in the northeast there a bit. It's actually pretty well positioned until the moon starts to come up. But it's a fairly large moon, so you'll lose a lot of the faint meteors. And we calculated the rate of meteors that you would see last month, following the mathematics that they used to calculate the zenith hourly rate. Gail said it ranged through about 110 to 160, typically average at 120, but inside the city, that means you're probably only going to see about 11 per hour, and out at Glenley around 47 per hour, at least at the early part of the night. When it gets up higher, you'll see more, but then the moon will start to be coming into the sky after midnight. When we get into January, though, we have the quadranted, and that's actually about the same activity as the Geminids, around 120 per hour, although this one's quite variable in its performance. Sometimes it gets up closer to 200 per hour, and other times it's closer to about 80. But anyway, when you do the math on that, that's about 25 per hour out at Glenley in dark skies. There's a full moon with this one, unfortunately, so that's really going to cut back on the number of meteors that are visible. But because of its position, we're pretty well favored at our latitude to see it. We've been talking about Comet 3I Atlas, which is the interstellar comet that's moving through the solar system now. It's not very bright. It's already at its peak and coming down slightly, so we're looking at about 10 to 12 magnitude. So next little while, here's the track of it here in this green line, and I've marked its current position, which is in Virgo, very close to Beta Virginis. And it's moving up this way toward Regulus, which is in the constellation Leo here. So for the next month, it'll be moving across that distance. Pretty easy to find it where it is right now, and it'll be easy to find it when it's close to Regulus. But with that kind of magnitude, you're going to need to look at it with a telescope, such as the one at Glenley that we own. We have another comet. I wasn't going to say much about this one. It does get up around -8 on January when it peaks, but it's actually very close to Comet Atlas. And you can see that the Virgo is down in here and Regulus is here. So one comet is moving up this way along the ecliptic, and this comet is moving this way, and they're actually approaching each other as time goes on, although when they cross over, they're not going to be side by side. So this one is a little more reasonable target if you want to go looking for comets in the next month. And that's it for the last month of the year. We have the moon and the Pleiades, I mentioned before, are going to be close together December last day of the year. And before you go out, after you come home from whatever you're doing on New Year's Eve, you can stop and take a look at the moon and the Pleiades. It'll be easy to find because it's pretty big. So thank you.
Okay, well, sorry, I didn't mean to wake you guys up. No. Anyway, we're gonna take a break now. So if we can reconvene, it's about 10 after 8. Let's take a 25-minute break and back about quarter to, not that much. Okay, 20 minutes, and we have our main speaker on site, so we can begin sooner than we had scheduled here. So let's take a 20-minute break, and about 8:30. That works for everybody. Okay, see you in about 20 minutes. I get your.
Cameras on.
Get seated and into the right spot, enjoy our main presentation. We're fortunate tonight to have Danny Morse with us. He's the owner of a computer consulting business. And as a young man with a newly minted bachelor's degree in dynamics and control and aerospace engineering, Danny was selected for a NASA aerospace summer intern program and studied the feasibility of an alternate air data system for the space shuttle orbiter. After writing software for the first drop test of the shuttle Enterprise, he got to go inside mission control during that test, and his data was presented at the debriefing after touchdown. He completed a PhD in aeronautics and astronautics from the Stanford University in 1994 and set his sights on working for a forward-thinking company that thinks big, lofty goals, indeed wanting to improve the world through technology. His rich career brought him to a position with Google to work on this as a site reliability manager for worldwide production services. He's also been a consultant for NASA's Gravity Probe B mission testing, Einstein's general theory of relativity, and for the ground-based testing of flight software for the Chandra X-ray Observatory. He has experience with computing, network infrastructure design, and developed the MA SysTools software package to configure and manage Unix, Linux computers. Danny is pleased to share his experiences and personal interests in astrophotography and eclipse chasing in person here with us tonight. Join me in welcoming Danny to our meeting. Thank you. Okay. Thank you.
Is that good? Can you hear me?
Yep, just good.
Camera's right there.
Okay.
Thanks.
Well, thank you for inviting me here. It's a pleasure. This talk is probably a little different than many that you've seen or heard. Judy Anderson overheard some of what I talked about from my career on an eclipse trip last year and suggested that I come in and give a talk here. So I'm going to start out with here's the outline. I'll give a little bit of talk about my background, early college days, and then what I did at for the internship at NASA. I ended up selecting a position after I got my master's at TRW Space and Defense Systems, and I'll cover some of that, and worked on 3 NASA missions while at TRW. And they was awarded a fellowship to attend Stanford for my doctorate. And that kind of had a profound impact on my life, that experience there and the connections that I made. I consulted for the NASA Gravity Probe B program for over 10 years, basically managing the infrastructure used for Mission Operations Center to control the spacecraft. And one day out of the blue, I got a call from Google and ended up working there, and that's where I retired from in 2013. As a hobby, I started chasing total solar eclipses in 2008, and I'll cover some of that, and just astrophotography in general, and my experiences traveling to the southern hemisphere to see the southern skies. Little background, I was born and raised in central Pennsylvania. I was an average student in high school, never made honor roll. But I knew pretty early on that I wanted to go to college. And actually thought I wanted to be an astronaut. I applied to the Air Force Academy and got a nomination from my Pennsylvania state senator. Was sent down to Naval Air Station outside of Philadelphia for all kinds of physical tests, x-rays, all kinds of exercises and stuff measured for a cockpit. And ultimately, I did not get the appointment because my high school English grades were too low. I did not apply myself there. I was into all the sciences, but history and English, things like that. I just didn't apply myself. And that's why I never made honor roll in high school. The one thing that was interesting in my senior year, after I learned some of the physics, Newton's equations, things like that, I got pretty excited about that. And I was already interested in software and had a course in Fortran the year before. And high school, this was in 1972, we had an old teletype terminal with a connection to a mainframe at a local college. And I came up with the idea of if the moon stopped orbiting the Earth, what would happen applying these equations? What would be the kinetic energy when they collided? So that's what I ended up writing a little program for, doing a digital simulation my senior year in high school. And I spent weeks and weeks of my free periods on this teletype system trying to write this program in BASIC, basically doing digital time steps and recalculating every time to tell when the Earth and the moon collided and what would be the kinetic energy. The point of bringing this part up is when I showed this to my high school physics teacher, he said two things to me that stuck with me. He said that if I knew calculus, I could calculate this exactly on a sheet of paper instead of all the time I did trying to come up with a digital simulation. And the second thing he said to me was, if I applied myself to 10% of my ability, I could do anything. And I never forgot that. It motivated me to do better. So I selected Purdue University to go to school. I liked the environment. I did very well. Math classes, I learned calculus and I just ate it up. I did make Dean's List every semester except the first one. Funny little story here is being an average student in high school and at the orientation for freshmen, my parents were there. And the speaker mentioned to the parents that if your student was A, B in high school, expect B's and C's here. And my mom didn't tell me this at the time, but she was pretty worried that I'd be home by Christmas. Dropped out, so flunked out. I received grants and scholarships that paid for my education, all through bachelor's program. And I did decide that I wanted to do the master's, and I found out that NASA had a summer intern program, but you had to be continuing on for an advanced degree to apply for. So the thing that surprised me when I talked to my counselor in the aeroastro department at Purdue, I was a senior there getting ready to get my bachelor's degree, and he discouraged me. He said, "You're wasting your time unless you're female or black." And I thought, that's crazy. I mean, all they can do is say no. So I applied. I was selected. I'm one of 50 out of 1,000 applicants, and it was a great experience for me working there. My degree and emphasis was in control theory at the time, but the only opening that they accepted me for was in fluid dynamics, which I had a minor in. And I ended up working on the air data system that was used to land the shuttle. And had to do a post-flight briefing, so I had to be in mission control to collect the data at that time. And what they were really doing was testing me to see if I was somebody they would really like to hire. And it went very well. It was one of the highlights of my career. During that first test flight, so the shuttle Enterprise was never intended to go to space. It was designed only for the approach and landing tests. And Fred Hayes of Apollo 13 fame was the commander and pilot of that flight. And there's a link here to the YouTube video of that. It's about 15-minute video of the entire drop, which there was the release of it. So I went on and completed my master's at Purdue. I did do interviewing when I had my bachelor's, and it was a great experience, and it was a free way to travel around the country to be interviewed. The companies back then, I don't know if it's still the same today, but they would come to the university for job recruiting days, and so it just was very easy to apply for interviews there and then follow up. When I was interviewing after my master's, I had two questions I always ask. Did the company have a PhD fellowship program? And if they did, would they send me anywhere I wanted to go? And there were two companies that said yes. They all had fellowship programs, but there were two that said, yes, we'll send you anywhere you want to go. And that was Hughes Aerospace and TRW. And I just, interviewing with TRW, I liked the people that I interviewed with a little bit better. Hughes actually offered a little bit more money for the job, but I ended up selecting TRW partly because of the type of spacecraft that they designed, which were 3-axis stabilized. And that was a little more challenging, and I preferred that. These are the missions that I had some impact on. The first one is COBE, which was the Cosmic Background Explorer, to measure the cosmic microwave background that was predicted. This is the one that I actually applied my control experience when I worked on this. We'll talk a little bit about that. For the Compton Gamma Ray Observatory, I was mostly writing simulation software at that time. One of the things that was problematic back in those days was that each person was kind of writing their own program for simulation, and somebody would copy from one person to the next for a different program. So the code was very hard to maintain. It was inefficient in terms of how we designed stuff that way. So I started working on software that had a defined application programming interface, or an API, and compiling and testing these into shared libraries that everyone could reuse instead of just copying source code around. Chandra X-ray Observatory, I had two roles in that. One was software engineer for real-time systems for the control system for the spacecraft. And the second one, I was also writing automated infrastructure to manage the general purpose computers at that time. So the test setup for Chandra was the real-time control system, various pieces of hardware that were integrated with it without the spacecraft itself. And TRW would use that as what's called a fixed base test. And the computers that were running that were Sun Microsystem workstations at that point. And they were shipped back to the Harvard-Smithsonian Astrophysics Lab in Massachusetts. And I ended up having to go back and do the training for the personnel to know how to run that entire system. So that was my involvement there. Gravity Probe B, I was responsible for all the computer infrastructure that was used for the Mission Operations Center and the Science Net for that program. I'm not going to say anything else about gamma ray or X-ray, but I'll go into a little more detail about COBE and Gravity Probe B. So this is more of the science part of it. And I will reiterate that I'm an engineer, I'm not a physicist. I didn't work on the science side of this, but these were some of the results that I found to be very interesting and really kind of groundbreaking, I guess. So in 1948, Alfred and Herman predicted with quantum mechanics, by basically running time backwards to right after, essentially after the Big Bang, 380 million years after the Big Bang. the universe became transparent. And they predicted that there should be an afterglow from that. And with the expansion of the universe, it should be redshifted from visible light and ultraviolet into the microwave. And the paper was really ignored for many years until 1964. Two scientists from Bell Labs observed this persistent hiss of background noise everywhere they looked in the sky. And that's when they started taking notice of what this was. So COBE was designed to image the entire sky very precisely. The spacecraft operated for 4 years. There's a little diagram over here of the orbit. So it was in a polar orbit. It was always almost perpendicular to the sun, and the spacecraft itself was always pointing away from Earth to survey the entire sky. Few details about the attitude control system to maintain that orbit. There were angular momentum wheels that were used to torque the spacecraft to keep it pointed where they needed to be. Reaction wheels will eventually become saturated if they're spinning up in the same direction. They'll have a limit on how fast they can spin. And what's used to unload that is magnetic torque rods that are in the spacecraft, and they use the Earth's magnetic field to torque the spacecraft the other way. And that's all you need is electricity for that, where if you were using thrusters, that's a finite resource, so you can expend all the propulsion system. So this is really the end goal of COBE and the results that they were looking for. So before this mission, the background looked perfectly smooth. They couldn't see any deviation in the temperature. And this was able to sort that out. And the idea was, if the universe is completely uniform, why do we have galaxies and stars? What would cause that to happen? And if it was not perfectly uniform, if there were variations in temperature, there would be density variation, and that would allow gravity to coalesce into what we see today. And this was a pretty amazing prediction using quantum mechanics and running time backwards to what the early universe should have looked like, and then using expansion rate to look at the effect of the redshift over that time. The measurements were pretty precise, plus and minus 0.02 of a Kelvin. And they did averaging over the 4 years then. And so that was in the range of 30 to 40 microkelvin. And then so the red is hotter and more dense than the blue. And that would allow gravity to affect those regions and form large-scale structures that we see today. So that was the theory behind it, and that's still currently what we're using. The background radiation follows a black body spectrum. Black body is an object that absorbs all the radiation into it and radiates back at a constant temperature, and ends up with a spectrum. The two key scientific researchers, Mather and Smoot, they were awarded Nobel Prize in Physics in 2006. There's a video of George Smoot giving a talk. I left a PDF of this talk with you, so these links you can access if you want to. It'll be in the PDF. To me, this was a pretty amazing prediction that seems to have been borne out by measurements. And also this year is the 100th anniversary or the centennial year of quantum mechanics. Started in the 1900s, early 1900s. I threw this in the SIL I'm going to talk about with X-ray observatory just to show with X-rays, they tend to penetrate through things. So how do you focus it to a sensor? So it was long and slender, and they used these conical shells, and the photons, X-ray photons, would bounce off of them and glance, and it would change the angle to direct it back in towards the sensor. For the fellowship, it was a pretty good program, 4 years, and I maintained all my benefits, seniority, pension, all. It was like I hadn't left the main campus when I went back to school. And I saw things there that were far ahead of what we were already doing at TRW, for example. So this is where I started getting more and more involved in software engineering and computer hardware and things like that. It was a very exciting time in the 70s, or this was in the 80s and 90s, being at Stanford. And Stanford University has a philosophy that's kind of different from many places. They encourage people that have ideas to start their own company and don't demand royalties from those people or those companies. They eventually get the money back as contributions later on. So Hewlett-Packard was probably the first company that was well known for that in the 1930s. The rest of these companies all came out of students at Stanford. Cisco Systems for networking, Yahoo and Google. In fact, Sun Microsystems, the first processor board, was built on campus, and they named the company Sun, and Sun was for Stanford University. I also met my wife while I was there. The interesting thing with that was once I finished my PhD, she wasn't crazy about moving back to LA. And so I mentioned that to my manager, and he said, well, we don't want to lose you. So he set up a situation where I could telecommute and have that. I did that for over 10 years. So around 1995, I became involved with the Gravity Pro B program. A little background on it. The idea basically is to use gyroscopes in space to test Einstein's general theory of relativity. And the idea is that there's perfect gyroscopes with no external forces or torques on them. If Newton's laws are correct, the gyro's direction will never change. And if Einstein's general theory is correct, gravity will warp space-time around the Earth due to its mass. And additionally, a spinning mass will drag space-time with it. It's called frame dragging. So the gyroscopes, this just some of the general achievements that they made. The gyroscopes for Gravity Pro B were 1,000,000 times more accurate than the best inertial measurement units that we had, which are nuclear-powered submarines. To make this work, you need a satellite that's the term is drag-free, and I'll explain a little more detail of how that works. It was pioneered at Stanford and perfected there. The other unique thing about this spacecraft, it's all immersed in about 2,400 plus liters of liquid helium at 1.8 Kelvin. So everything is quite chilly, and the dewar is not perfectly insulated. So there is helium boil off. And what they did was use that with the thruster system. And I should back up with one comment. Every other satellite system that I've worked on use on-off thrusters. In other words, the valves either open or close, full on or full off. And the typical forces for that are 1 to 4 newtons. And if you did that on this program, one firing of one thruster would ruin the experiment. It would be over. So they designed a proportional thrusting system, and it's normally balanced. So helium is leaking out both directions, and the force is balanced. So there's no thrust. And if you need to correct for something, you just move it's like 2 needle valves pointing towards each other that are connected, and you just move them one way or the other to create a net force from the helium boil off. Just for reference, there was a gravity probe A, which was on a sounding rocket. And the idea for that was to measure the predicted dilation of time that general relativity predicted. And one interesting tidbit is that GPS satellite clocks, because they're above the Earth, there's 2 effects. Gravitational field slows down time. So the farther away you are from it, the faster it goes. The faster you move, the slower time goes. And in the case of the GPS satellites with their altitude that they're at and the velocities they have, they actually go faster than clocks tick on the surface of the Earth. If that was not, and so for your smartphones, for example, that is calculated using Einstein's equations, so that the time signal that you get for your GPS signal to your smartphone has this calculation put into it, so that it agrees with the time on the surface of the Earth. If that was not done, the rotation of the Earth would have an effect in east-west that you would be off by a couple of blocks, for example, at these latitudes. So here's an illustration of what they're trying to measure with gravity probe B. It's in a polar orbit at an altitude of over 642 kilometers. And there is, I'll go into a little more detail of these parts and the components in the spacecraft in a slide or two. They have a telescope on here that points to the star IM Pegasus as its reference. And they're measuring the gyro drift relative to that. And there's 2 effects predicted by Einstein. The geodetic effect is just from the mass of the Earth. And it's in the plane of the orbit, in this case, pointing down over here. And then the frame dragging effect is because of the rotation of the Earth. It's like a spoon in molasses. When you turn it, twist it, it drags space-time with it. And the equation for it is down here at the bottom. So this first part is called the geodetic effect, which is just due to the mass of the Earth. And the second part over here is the frame dragging. And that frame dragging is about 170 times smaller than a geodetic effect. So it's much harder to measure. And there's some numbers in here for the milliarc seconds per year that you're going to get from this. The spacecraft operated for about 16 months, essentially until the helium all boiled off. And once the temperature rises, the experiment's over. And they did 4 months of calibration and then 12 months of operation for collecting data. The only thing I really wanted to point out here is the key part inside the spacecraft. Here's the door that's filled with the 2,400 liters of liquid helium. And down in the middle here is where the instruments are buried. So the gyroscopes are here. There's 4 of them. I'll show you more detail about that on a slide or two later. This is the telescope that's made it to it. And that's really the important thing I wanted to point out here. This is an image of the gyroscope. They're about the size of a ping pong ball. Solid fused quartz, made as round as they could. And then it was coated with a very thin coating of niobium. And niobium at 1.8 Kelvin is superconducting. So one thing you might ask yourself, if you have a perfectly smooth ball or sphere with no markings on it, how do you tell which direction it's spinning? Well, it turns out there is a property from a superconducting material. I'll get to it in the next slide after this. This is just a little bit. So there were 4 gyros. The first one, gyro 1 in the front here, and then 2 in the other axes. There is a compartment here for what was called the drag-free proof mass, and it wasn't actually, there were problems with that. It wasn't worked. It wasn't used for the drag-free motion of the satellite. What they ended up using was gyro 1. And the idea of drag-free is this gyro is in a housing. They use electrostatic pads to keep the gyro from hitting the side of the housing to keep it centered. And using that measurement, they then use the thrusters of the spacecraft. So let me back up one step. For drag-free, you put a proof mass inside the spacecraft, and you are then it's protected from any external forces like atmospheric drag. It's small at those altitudes, but it's still there. And there's solar radiation, solar winds that impact these spacecraft, push on them. And if you thrust against that so that the proof mass is basically in pure free fall in orbit around the Earth, then you end up with what's called a drag-free satellite. You've eliminated the effects of the drag or other external forces on it. You eliminate that, and the spacecraft will follow a perfect orbit around the Earth. This is a photo of the assembly for the gyros, 1, 2, and there's 3 and 4 here. The proof mass was down here, and it wasn't a system. It just turned out there were operational problems when they got on orbit, and they ended up using the first gyro instead of a proof mass to follow to create the drag-free orbit. So to answer the question about how you detect the spin axis, when a superconducting material is spinning, it creates a magnetic moment called a London moment, named after the person who discovered this. A system to do the readouts was basically a coil around the housing, and they used a quantum interference device that was most sensitive magnetic detectors in existence. They could detect changes in angle of 0.0001 arc seconds. And this would be equivalent to seeing a human hair at 10 miles away in terms of the angle. The gap for the rotors was thousandths of an inch, 32 microns. And the rotors for these gyros, they're calling the gyroscopes or the rotor, are roundest objects ever made, at least up till the time they were built. I don't know if any since then is more round or not. And if you blew one of these up to the size of the Earth, the distance from the highest mountain to the lowest valley or deepest ocean trench would be 8 feet. So I'll give you a little idea of the scale. I mentioned briefly before that the thrusters use the helium gas that's continually evaporating, which means it boils off. And the thrusters then used a proportional valve to control the thrust. The force of the thrust was a few millinewtons. Earlier, I mentioned that typical on-off thrusters that are used on satellites are 1 to 4 newtons. So this is many orders of magnitude less. And I already talked a little bit about the drag compensation. And I guess the last point here is that this was the first time ever that a spacecraft was controlled in all 3 attitude, axes and also in position. XYZ position to do the drag-free orbit. Normally on orbit, we're doing attitude control. There are maybe course corrections and stuff for the deep space probes, but that usually is not something that we would do in Earth orbit. But it was needed here for the drag-free characteristic. So the whole idea was in drag-free, there's no external forces on those gyros. So if Newton's right, they should not change their angle. This is more what I was actually doing on the program. I was there to use the software that I developed to automate the computer infrastructure, basically. And so after the 9/11 attacks, NASA was much more rigorous about their testing for security of the computer systems before they let them connect to the IO network. NASA has two IO networks, one for unmanned spacecraft and another one for manned spacecraft. So they did their scan. They had two network services that they asked us if we were using them, we were not. They said, would you turn those off? So I made the changes. We pushed them out. 20 minutes later, all the systems were updated. And they retested and we were good to go. Lockheed Martin was a subcontractor for this program that built the spacecraft itself. Most of the science instruments were designed and built at Stanford. And so there was a set of computers at Lockheed, similar to what we had at Stanford. NASA tested them because they wanted those to connect to the IO network as a backup. And NASA said, hell no, because they were wide open, root administrator access on all the computers. And this is kind of how these Sun OS and Solaris at the time were installed out of the box or off the CD. Everything was enabled, so you had full access to all services without doing anything, but it was completely insecure. So the IT people there didn't really know how to fix it because when they built their computers, they would go around to each one and put a CD in one by one and manually type all the stuff in. And it's very error prone, inefficient, and they had the default configurations for everything. And they hadn't even applied any of the recommended or security patches, which were freely distributed by Sun every month. They weren't applying those either. So the solution we came up with was ship them to Stanford. We put them on our network, reimage everything with our software or my software, and re-IP'd them back for the network infrastructure at Lockheed. And NASA rescanned and retested them, and they were good to go. Here's a photo of Mission Operations Center. And so we can, I don't know if you can see the pointer here. So there were 5 Sun workstations, 2, 3, 4, and an SGI. There might be another Sun here. So there are 5 Sun workstations and a silicon graphics box, which was used for the graphics processing because they had, back then, silicon graphics was the most efficient graphics computers you could typically get. And this was during a dry run for launch. So there's one, and they called these clusters of machines was called a pod. And they were independent. They could control the spacecraft in all aspects and collect the data that they needed from telemetry. And there was an identical system over here. There were 5 of them here. And we could switch back and forth if there was a failure on one, disk failure or some type of hardware failure, whatever. So there was backup that could have almost instantly switch over to control the spacecraft. And while we were doing the dry run, NASA said, well, it would be really handy to have another monitor up here to display some information we want to see up on this shelf here in the top. And so the IT guy, the IT manager on the program for Gravity Probe B, Jeff Wade, he went and pulled the computer out of storage, and I added the host name and Ethernet MAC address and those other things into the database. And on the Sun systems, the equivalent of what you would see in a BIOS today on a PC, had an OK prompt, and this was the exact command you would type to boot over the network, install the partition the disk, and then install the operating system. And then it configured itself with what we had configured on the master servers. All the recommended security patches were installed, and 90 minutes later it was ready to be used. And NASA was expecting that the next dry run it would be there, not that same day. So that was they were impressed with that. Here's a photo of the spacecraft. Give you an idea of the scale. There's some people down here working on it at the bottom. This is getting ready to button it up with the other fairing for launch. It's already made it to the booster. This is a photo of this is hanging in my hallway in my house. And the text at the bottom here was a real compliment to me. Francis Everett was the principal investigator for the program, and the thing worked flawlessly. We had no failover, and near the end of the mission, NASA requested that we do a failover to show that it actually worked, and it did. And then we switched back, but there was no fail on any of the computers the whole time. Here's some references, and these are in the PDF if you want to search for a little more information on this. And the YouTube video here is about an hour long NASA presentation with the various key people on the program of the final results. So in 2002, Northrop Grumman bought TRW, and I knew that I was going to leave. I didn't like the new management structure, and it was kind of getting time to leave anyway. And out of the blue, I got a call from Google if I was interested in interviewing. And it was two colleagues that were in the aerospace robotics lab at Stanford. Were now working at Google, and they recommended me. When I went in, well, I had a phone screen first, and then had an on-site interview. And at TRW, I was kind of the Unix guru. So I probably had a little chip on my shoulder. And I went in there thinking, what do they know that I don't know? Well, they knew a lot that I didn't know. I did pretty good on a number of questions, but there were a couple I didn't do very good on. And I went back home thinking I might not even get a second call. But I did start reviewing algorithms and some of the things I hadn't thought about or looked at for quite a while, and prepared. And I did get a second call. And to go back on site, because I lived nearby. This was not like I had to do everything in one day. So I was invited back, and this was on the second interview. My favorite question was, I've got 20 terabytes of data to compress, and I start the process, power goes out, and the emergency generators kick in. How much fuel do I need in the generators to complete the compression? And part of it was my aerospace background instead of just pure computer science. The guy interviewing me thought that was a fair question. And I grew up around farm machinery and stuff, and I worked on a farm for my summer job at Purdue. And that actually helped me because I knew about how many horsepower it took to turn a generator to do so many watts of output. And so and the guy wasn't looking for an exact answer. He wanted the thought process and how I thought about solving it. So it's basically, let's chunk this up into a bunch of different things. And this was computers at the time in 2004. How many do you need? How much time does it take to do the compression? And how much power does each computer use over that time? And so you get a total number of watts, you can convert that to horsepower, you can look at it, how much an engine would, how big an engine you need to generate that many watts to power it. And I came pretty close, and I aced that one. So Google was the first company to create a position called site reliability engineering. And prior to that, companies would typically have an operations center, maybe sometimes it's just called a network operations center. An alert or a page comes in, and they would have more junior people there. And if they could solve it, fine. And if not, they would escalate to a more senior engineer. Well, that took time. There's communication problems sometimes of describing the problem. And Google said, we don't want that kind of downtime. Every millisecond counts. So they created this position, and they put people in there that could solve the problem without, there's no one else to escalate to. We were it. So now every major tech company has an SRE position in there. And so this is people that are running production services is where this is used, where every millisecond or second counts, so downtime. It was a fun job. I got in, I started in March of 2004, and there were about 1,500 people worldwide at that time. It was dynamic, it was exciting. Change was happening very rapidly. Growth was happening very rapidly. There were a lot of really brilliant people, probably the smartest people I worked with, other than maybe the people in the lab at Stanford. I was when I did my PhD work. No software changes were done without peer review. Everything had to be checked. So it was, I liked that environment. They were doing software development like I always thought it should be done. They had guidelines for every language, so style guides, and you had to follow it. And everything that was part of the peer review process, where you also following the style guide. It wasn't just is the code accurate. And the idea was then other people could read your code if they didn't use the same, if they had a different style. It may not have been the best in all aspects, but it was common enough across the entire company that everyone could function more efficiently with anyone's code. Another thing that was different was peer reviews and performance evaluations were for the annual reviews. Your peers had a lot more input into your performance than your managers did. Your managers maybe had 10%, 15% of the say. And I like that. Instead of a manager, you could have a manager that gets into your career in many companies. The other thing was kind of unique is the pay scale was more like pro athletes. So I could have the same job title as somebody else. And if that person is just doing amazing things, coming up with Gmail, for example, they may make 10 times what I do. And I appreciated that. I didn't have any problem with that. One other thing that was kind of unique at Google, 20% of the time, 1 day a week, you could work on anything you wanted to, as long as it potentially benefited the company. And you could pool these up kind of like vacation hours and then just take a week and go do something. And this is how Gmail started. The guy did not like how current email programs worked, and he wrote Gmail and started sharing it with his friends and got some other people to use their 20% time and kept developing it for a while, and it started to look promising. And then they would do an engineering review with usually a more senior vice president of engineering. And at that point, if it was deemed a potential asset to the company, you could get funding, and people were allocated to actually work on it as a project. And so I started in late March, I think March 27th of 2004, and Gmail was launched April 1st, 2004. And Google was well known for their April Fool's jokes, especially back in the day. And so Gmail launched with 1 gigabyte of free storage. And everyone thought it was a joke because back in 2004, if you had 100 megabytes, that was a lot for a mail, for like Outlook or Yahoo. And so everyone wrote it off as just an April Fool's joke. There were a lot of nice perks too. 3 meals a day, free, professional chefs preparing them. The Food Network came in and videotaped some of our lunches for their programs. We had free gyms, there were free doctors on site. I used the doctors primarily to get my travel vaccines and stuff like that. It was very convenient. They had nap pods. They encouraged you that if you're tired, don't just sit at your desk like a zombie. Go take a nap and come back and do something productive. TGIF, thank God it's Friday every week. And we'd have hors d'oeuvres prepared by the chefs or the cooking staff, beer and wine. And then the founders would get up and talk about what's happening, and we could ask questions afterwards. So there was a lot of give and take. Pretty much everything was fair game in terms of questions and stuff. It's not like that anymore. They're a much bigger company, and things don't work that way anymore. Oh, and the best benefit, free full body massage. That was not free though. It was subsidized, but it wasn't free. You had to pay a little money. So when I started, there were 12 of us. How am I doing on time?
Yeah, well, 20 minutes, Tim.
Okay. Because the rest of pretty much the rest of this is photos, and we'll go through that quickly of travel and eclipses and stuff. I guess the only thing I want to mention here is about 4 or 5 weeks after I started, so early May, I went into one of my weekly staff meetings, and on the agenda, second or third bullet was Denny's issues. And I didn't recall telling anybody about my issues. Well, it turns out that we were getting ready for the IPO in August, and the initial amount of money that the 2 founders, Larry Page and Sergey Brin, the initial money was given to them at a Denny's restaurant in Sunnyvale. And so that was the code name for the IPO. When I started, we were doing 24-hour shifts. This is the first time I ever carried a pager. But this was for production systems, for Google search, for images. There were only about 4 services at this point in 2004. Now there's thousands of them probably. Our group, we had 3 minutes to respond and acknowledge a page that we were in front of a computer working the problem. So it could be pretty stressful when things were breaking all over the place. We had a motto that hope is not a strategy. We had a weekly wheel of misfortune where typically more senior people would come up with a situation that potentially could happen. And somebody would be picked. This was all out in the open and around our offices. We just collect out in the common area. And you would have to, they would give you the conditions of what's happening, and you had to solve it on your feet, basically. And you could ask questions of, did I get an alert for this, or such and such? And the person posing this problem would answer yes or no and stuff. So you could work through it that way. But the whole idea was to train you about things that either had happened already and wasn't widely known, or theoretical problems or hypothetical problems that could happen. One of the times I was on call, we had one fiber optic line to South America from Miami, Florida to probably Rio de Janeiro, someplace in Brazil. And when that line went down, we pretty much lost all of South America, which wasn't a huge market at the time. But this was the first connection that we really had to that area of the world. And so the alerts started going off. And long story short, a farmer was digging a hole for his dead horse and cut through the fiber. And then the last thing I'll mention here is in 2010, the Beijing office was hacked. It was a bug in Windows XP Internet Explorer version 6 or whatever that Microsoft didn't even know about. And they got in and eventually they hit a tripwire that we were alerted. And the reason I mention this at all is unlike what would happen even at Tier W, for example, where something's been hacked, they would patch it, kind of sweep it under the rug and move on. Google declared a code red. The founders and top management handpicked 100 or so engineers, and they spent the next 3 months on a floor in one building every day, 16 hours a day. That was their only job, to go through the logs and reconstruct exactly what happened. And we redesigned almost everything about authentication and login and access to production so that that couldn't happen again. And it hasn't. So as we grew, I ended up on what we call traffic team. We were responsible for the overall health of production. We were considered the SRE team of last resort. So other SREs could page us if they couldn't figure out what was wrong with their systems, and kind of how am I supposed to know what's wrong with your system? But they were allowed to do that. And most of the outages were caused by human errors, not hardware errors. So I would tend to pick my on-call shifts for the weekend when people aren't breaking things. Eclipses. So I'm only going to talk about 2 of these, and mostly with pictures. So we'll go through this quickly, and we can stop if I run out of time. The first one, my first eclipse was to the North Pole, and a week after that was an eclipse. And then here's the rest of them. I was rained out in 2009, but the rest of them I've seen the corona, and these are just total eclipses. And then I'll spend some time talking about Union Glacier, Antarctica, which was a fairly unique experience. So the North Pole, we flew into Helsinki, had a charter flight to Murmansk, Russia. The red path is the path up to the North Pole, and the lighter blue is back. We stopped on the way back to around the Faroe Islands. That's this area here. Svalbard is over here. This is a island that belongs to Russia, and that's where they did a lot of their nuclear testing. So it's highly radioactive. You can't go there. The point right here, though, where we got close, that's where we observed the eclipse. This is a view from the North Pole, north looking down North Pole. Same red up and blue back. These are just GPS coordinates I had on a Garmin, and you can upload them into Google Earth and create plots like this. And you just spin the Earth around, you see it whatever orientation you want. The ship we were on was a nuclear-powered Russian icebreaker. Being an engineer, I was interested in trying out a nuclear-powered ship. About the size of a destroyer. Total horsepower, 75,000 horsepower with 3 electric motors. The reason I show this is these props are replaceable at sea. They carried these on board on the back deck. I'd hate to be the guy that had to go down in the water and put these on, though. This was a view from the bridge. They had carried a helicopter on board, and when they weren't using it to survey ice of where they wanted to go to give the captain directions for the best path forward, they would give us rides in a helicopter a couple of times around the ship and at the North Pole. The bridge was open 24/7. You could go up there anytime and hang out. I took this photo from the helicopter of it crushing ice. And this was the first one they had with kind of a spoon-shaped bow, and it rides up on the ice and just crushes it down and breaks it. We saw a number of different polar bears. When we arrived at the North Pole, it was 1:30 in the morning, local time. Or no, it says here 1:53, so. The weather was perfect. So in the summertime in the Arctic, there's a lot of evaporation, so there's a lot of fog, drizzle, things like that. We had perfect weather the day we arrived in Murmansk. We had perfect weather at the North Pole, and we had good enough weather to see the eclipse. And those were the only days it was clear like that. The rest of the days were fog or drizzle. You can see the air temperature there, no wind. It was quite balmy, really. So we made it. We all gathered in the front of the ship. I'm right here in the middle. And the symbolic circle around a globe. Oh, the name of the ship, this is in Russian here, but it's 50 Years of Victory from World War II, what they named the ship. And a few people decided to go into probably about half the ship. You had a strap attached to you, so you're coming out one way or the other. And the sea ice has more needle-like, it's sharp. And two people dove in instead of jumping and hit one of these blocks of ice and needed stitches in their forehead. There's the helicopter where we're getting on board. So they needed a stable enough place where they could land the helicopter on the ice without breaking through. We were on the ice for about 8 hours, almost 8.5 hours. They had a barbecue out there for us, which is this area over, where's my cursor here? We set up over here for barbecue. People just hung out, walked around. Right here. They always had 3 riflemen forming a perimeter for polar bears anytime we were off the ship. And I like this just because of how flat the ocean is. Kind of out in the middle of nowhere. So this was my GPS data from where we were at the North Pole. And then it took about an hour. They came down and parked the ship in the ice here because they had to find a place where it was safe for us to be out and about on the ice. And then the rest of this is drift over time, parked in the ice. And so right here is where we got out on the ice. And then we got back on right here. And I have the numbers up here for how far we drifted over that time. About 2.1 kilometers in 8 hours. And then we started heading south. Part of the reason I was so interested in this trip was as a kid reading Call of the Wild and wanting to see the midnight sun. So I finally did. This is our location for the eclipse. There were clouds. At the beginning stages of the partial, it was pretty clear, it looked good, and then we had some clouds move in. And the captain was, he was more worried about getting back to port because they'd only dock at high tide. And Rick Feinberg was our professional astronomer on board. And he told the captain, that is the way back. And we ended up flying speed and we broke through right before totality started. So I took this off to the side a minute before totality and same exposure a minute later. And that's kind of how a lot of people felt afterwards. So Union Glacier, this was a very unique experience for me. Total 70 guests. The temperature ranged from, slightly above what we do is 0 Fahrenheit to, slightly below the whole time. The camp area has a mountain nearby and it's protected from the wind, so it wasn't so bad. We did excursions each day before the eclipse. And when the winds kicked up, it was cold. We slept in unheated tents. They were double layer, so that insulation actually worked very well because the sun's up 24/7. And as long as it's not too cloudy, that worked pretty well. The average temperature was probably 12 to 14 C in the tents. They were built on top of a 4x8, almost like an insulated door that they'd lay on the ice. They put the tent on top of that, and they had 2 cots in each one and sleeping bags rated to 40 below. And so it was pretty comfortable. The thing that I had problems with was depth perception because I had no frame of reference, trees, houses, roads, and everything looked closer to me than it really was, by a factor of 5 in some cases. So there's the tents behind us. There were 35 of them, 2 per tent, so that's why there were a max of 70 guests. We landed on a Boeing 757 on a nice runway. And this camp is here because they have an area that's called blue ice, which is, to me, I read it as very dense ice that's capable of handling large aircraft like this. And it just occurs naturally in this area. So I thought this was set up to play. No, I tested it at home and it worked on a Mac, but there it goes. So this is like 3 minutes of landing. Is there any volume on this?
No, not really. It will be difficult right now.
Let me unplug it if you don't mind. I'll just.
Don't worry about it.
Okay.
Science.
Okay.
There's not a whole lot to it. I'll narrate. The main reason to show you this is it gives you an idea of what the whole area looks like because we do a 180 at the other end of the runway and I video the whole thing. This is completely visual landing. There's no instrumentation on the ground for landing. And so if they don't have 20 miles visibility, they don't take off from Punta Arenas, Chile, which is where the flight comes from. Prior to they got the 757 in 2016. Prior to that, they were using a Russian cargo plane. And the plane had to be refueled in Antarctica, so it had a point of no return. The 757 can go down and back without refueling, so that's kind of nice. So here we are coming in on the runway. And you'll know when we touch down because I bounce around.
Is that a charter flight or a regularly scheduled?
They own the company that operates this this camp is Antarctic Logistics and Explorations, ALE. They're based out of Utah. And they own the plane and they hire a crew to fly it, which is Icelandic Air was the crew that was on it. And we had flight attendants in addition to the pilots. And she, when we get up here at the end and get ready to turn around, she made the announcement, keep your seatbelts on until we tell you all the stuff you'd hear on a normal flight. So the vehicles out here are just people to meet us. They do groom the runway to rough it up as much as they can. And you'll get a pretty good view of the ice here when we turn around because it's reflecting from the sunlight. So this is probably the best part about it. You kind of get a 360 or at least 270 of what it looked like down there. And this is all to encourage you people all go down there.
Wow.
No Zamboni.
And this is where they told us not to take our masks, because this is right after COVID. We had, I had over a dozen COVID tests just to get here, and they tested us once we got there too. And the flight attendant said to take your mask off, because when you get off the plane, if the wind's blowing hard, it might blow it off, and you don't want to leave those in the NRA. So this is pretty much it right here. Since there's no audio, this is where I terminated the whole thing. So that was what it was like when we deplaned. They had bikes that you could use, and they worked pretty well. There happened to be a 1956 Porsche there. And this woman started this project to raise funds to end child trafficking. And she had driven, this was her last continent. She had done runs on every continent, trying to raise awareness and funding for this. When she actually drove it, they replaced the front wheels with skis. This was our setup for Eclipse Day. It was about 17 or 18, minus 17 or 18 C that day. It was short because we were near the edge of the path, because it was not safe to move any place else. They used ground penetrating radar to map out the camp and know if there's any crevasses and stuff like that. So you can't go anywhere beyond those boundaries. But at least we were in the path. There were not many people that saw this eclipse with their own eyes. There were a couple of planes, I think. There were the guests and staff at this camp was maybe 150. There was a Chilean research group nearby with maybe another 30 or 40. And I think one cruise ship saw it, which is what Jay and Judy were on. And I think that's all that saw the corona. It was interesting because we were on the nighttime side of the globe, so the shadow moved the opposite direction of what you're used to. We can go back and look. Well, it's just an eclipse of the video. I don't know if you want to see it or not.
Sure.
I can go back to it real quick. The first video here, the 5-minute video, is from ALE, and it's worth watching if you're interested at all. They give you a complete overview of the camp and what they do there, and the other areas. They have an area where they can do mechanical work on machinery and stuff like that. They cover everything, and that's worth spending 5 minutes watching that. In terms of travel to the Southern Hemisphere, these are places I've been. Equipment I use nowadays is for the lightest stuff, which I use for eclipses now, is a Skywatcher Star Adventure mount, Nikon Z8, and I have a 600 millimeter lens f/6.3. It's very light, compact. I can get it all in a carry-on easily. If I'm going to go for a week or two to Chile, for example, I'll take the equipment in my check bag in a Pelican hard case. And after having problems with a counterweight in my check bag being taken by security in Costa Rica, I bought a strain wave mount and don't use a counterweight anymore. And I wanted to just bring this up briefly. So I like San Pedro. We were there with Travel Quest a year ago, and that was my 4th trip there. It's not that hard to get to. You fly into Santiago down here, and you can connect. There's flights every 2 or 3 hours from Santiago to a little town of Calma up here. And that's where when I go on my own, I rent an SUV usually, and it's a 70-minute drive or so to San Pedro. And so if you want to go, it's not that hard to get there. There's a fabulous place just south of San Pedro that's set up for astronomy, and it's dark sky. And the website's here, spaceops.com. They have permanent piers, concrete poured in a lot of places around there. They have equipment you can borrow, or not borrow, you can rent if you're going down there for that. They do have, usually, they have evening showings for guests. And that's usually over by 10 or 11, and then the rest of the night, there's no one else around. But what you do, they have 5 or 6 units there that you can rent, and the units usually are 2 to 4 bedrooms and a kitchen and living area. So you can get your family together or friends and go down and rent one of those units and just stay there. They have power to these piers, and they have good internet connectivity. I show this because when we were there last year, I just laid my pixel camera on a table that had a little hinge or notch on it that it could prop up on, no mount, so no tracking, and put it on a night sight, and it took 2.5 minutes worth of integrated data by snapping every 15 seconds, automatically stacking. And to me, that's not bad for a cell phone, just laying there, not on a tracking. And at the time anyway, it would do up to 4 minutes, and I cut it short. I didn't know how it was doing, and I thought I better check this out now, see if it's doing anything decent. The only thing I did manually here is I forced it to focus on infinity instead of letting it try autofocus. The next thing I did, this is a different trip a year before. I had taken, like Jay mentioned earlier, I have raw photos all over the place, and I hate post-processing. I just don't have the patience for it. It doesn't, I don't know, I just want it automated. And so last year, or last spring at the Northeast Advanced Imaging Conference, I attended a workshop for StarPix, which was brand new at the time and it just launched. It's subscription-based, so that could be one detriment to it, but this is one of those raw images. And I uploaded 26 and said, go. And 5 minutes later, it came back with that. I did nothing else. And there's, it's good enough. It's better than the raw. And I'm too lazy because I'd rather do other things. Editor, yeah. And then the last set here was Easter Island last year. And the only, I wasn't originally going to put this in, but the evening before the eclipse, Jay gave a presentation for the eclipse the next day and suggested that we try to do Bailey's beads, C2 and C3. And I never thought of trying there for an annular eclipse. A solar, yes. I mean, total, yes, but not an annular. So that's what the exposure looked like. But then when you crop it, there's a little prominence there. And this was stop down or faster exposure rate. The Z8 can snap the shutter pretty fast. I like that. It was worth doing. And I would have never thought of doing it without Jay's input or suggestion the night before. And the last photo here, this was the Venus transit in 2012 from Tahiti, where Captain Cook did his research and observations. Thank you.
Do you have any questions for Denny over here? It was an excellent presentation. Thank you very much. Yeah, you have a question?
Which end of the cable was the pole dug for the horse?
Which end of the cable was
Was it the Florida end or?
Oh, it was in Brazil. It was a farmer in Brazil.
Wow.
Yeah.
When it comes to the interaction between the engineers and the scientists, take the gravity probe B, for instance. I guess a lot of that was already sorted out and decided. For instance, the altitude of the orbit, etc. All of this must have been hashed out, wrangled over a bunch of stuff.
That was all determined mostly by the scientists.
Right. Now, my question, and how we've got it prepped, my question is, So the feedback between the scientists and what they wanted to do versus what you guys had to execute. How much feedback goes back and forth?
In that particular project, it was very fluid because the initial idea was in 1957. And two physics professors, there was a third professor that was initially involved, and he kind of dropped out of it. But there was a engineering professor from aerospace engineering, Dr. Professor Cannon, Robert Cannon, who was an expert in inertial measurement units. He had worked at Draper Labs in Massachusetts near MIT. And they brought him in for the whole idea because gyros are used in inertial navigation units. And that's when, well, how do we get rid of all these disturbances and forces? Well, one way to do it is to put it in space. Can't do it on the Earth. The forces are too huge. You'd never get the measurement you wanted. And so because of that, because Professor Cannon was involved and another professor, Daniel DeBray, was involved with the machining of the quartz spheres and the polishing. That was all done in the astro department and actually in a different building. But they were all, Cannon and DeBray were co-PIs on the program with the physicists. And so the communication was quite fluid in this case. There was no friction, or very little.
And now we're talking about the fused quartz. How do you get them up spinning?
Oh, I never mentioned it. That's very interesting. A very good question too. So first of all, the pieces for the housing, they were not glued together or screwed together or anything like that. The polishing of the surfaces themselves were so smooth, they just did molecular cohesion, holding them together. And that's how everything was fitted together from the different parts. And then to get the gyros went up static, and then on orbit, they spun them up because they had little channels in the housing, one little channel with helium. They would push it in there, and the boundary layer friction, it was laminar flow, would spin that gyro up in space to, I think, 4,000 RPM or something like that. Don't quote me on the RPM, I can't. And then it would shut it off, and they evacuated it then so that the chamber itself was pure vacuum. And it spun like that for the rest of the mission. There was some pretty ingenious things that were done for the mission, yeah.
Yeah.
Any other questions?
There's a question online from Zoom regarding the gyroscopes, if you know how they were protected during launch.
I think they were just laying in those housing because the clearance was so small.
Oh, yeah.
There was no caging that I know of. Yeah.
So what was the result, the scientific result of the gravity probe?
The geodetic effect was within 1%. The frame dragging, because it's so much smaller, I think they were like 15% accuracy range on that.
Did it follow what was expected, predicted by Einstein?
Yes, yeah, within that error bar. So the geodetic effect was within 1% or less than 1%. They had to do a fair amount of modeling afterwards because the gyros are perfectly, almost perfectly round when they're not spinning. But when they spun up, they bulged out like the Earth did. I mean, it's small, very small, but they had to model that to calculate any effect of that on the motion of the gyro. What was the other point I wanted to make? They delayed the launch by 6 months because there was excessive interference from the power supply for the spacecraft control unit. And they reworked it and reduced the amount to where, and it was partly, we got to get this program off the ground. It had already been 45 years or more going. It's the longest running NASA program ever. And so that there was still too much noise that affected the results too, more than there should have been. The other thing I didn't mention is they could only collect scientific data when they realigned with the star Pegasus, but it's orbiting the Earth and it goes into shadow. And when they're in shadow, you lose it and it drifts. And then they come out and they have to realign to the star and lock on before they collect data off the gyros again. Well, Lockheed was doing the attitude control system for the spacecraft. And those gyros were on appendages on the side. And they would flex from thermal when they went in and out of shadow from the sun. And that was stupid. It shouldn't have happened. So it took them longer to acquire the star than it should have. The last piece of this is they got the data from Harvard Smithsonian Astrophysics Observatory in Cambridge for the proper motion of IM Pegasus. So they had to account for that too, for the motion of the star over that year. So that it was a very precise type of experiment.
Well, even measuring the spin and not interfering with it while measuring it.
There is a slight interference when you
Okay.
measure it because of that coil,
Okay,
but it was minuscule compared to the measurement they were making.
okay. Thanks.
Yep.
Any other questions?
Yep.
Oh, go ahead, Michelle.
I'm just curious, what software programming language did you use for the system?
What programming language?
Yeah,
Most of it was written in C for the science mission. A lot of my stuff to control things is a combination of C and Bash shell programming and some Python.
Okay, if there are no other questions, this is a little token of our appreciation for it.
Oh, well, thank you very much.
Thank you. Thank you for coming. Yeah.
Lights on?
Yep.
Okay. All right, for those that are interested, we will be reconvening at Boston Pizza on Pembina Highway, a little bit south of us. And it'll probably take us, for those doing the technical work, it'll take us probably 10-15 minutes to clean up, but by all means, head over there. They are expecting us. So we'll see you there, those of you who decide to come. Thank you and have a good night. We'll see you next, I guess in January next year. Happy New Year, everyone. Enjoy your holidays.